We now take a look at our last geometric application of the definite integral, and this application is called arc length, right? So if you think about it, what have we done with the definite integral so far? Well, we've computed area, we've computed volume. It almost seems like it's a step backwards to talk about length, but partly, the arc length is usually one of the last applications you discuss, well, geometric ones anyway, because the formula is the most involved, and it's potentially the most tedious, depending on the amount of algebra that's needed, right? So, it's not that we're taking a step back. We're continuing to build on what we can do with the definite integral, right? So, what do we mean by arc length? Well, suppose I have a function, right? They all start with graphs. So we have y equals f of x, and let's say we know that portion of the graph is traced out as x goes from A to B, right? There's our x-axis, there's our y-axis. And essentially, we want to answer the question, how long is this curve? I mean, that's it, right? There's no fancy region or revolution or anything. We just want to ask this question, how long is this curve, right? And to give you a sense of what we actually mean, suppose this curve it just kind of lay in this squiggly fashion on the floor. It was like a piece of string. And if you could pick that string up and just pull it so that it becomes linear, and then you just lay it right next to a ruler, and you could see how long it is, right? But unless you have some magic power that I don't have, and it's quite possible that you do, I can't pick up this curve, right? I can't pick it up and straighten it out and measure it. But I'm still curious. I still want to know how long this curve is. So how could we possibly figure this out? Well, this is what we're going to do. It seems like in every instance, good old Riemann sums come to the rescue. Like whenever there's some quantity that we can't figure out, something that is somehow continuous, right? Whether it's a continuous area or a continuous volume or now a continuous length, right? Let's use the Riemann approach. And this is what we're going to do. We start with our partition, as usual. And then, based on this partition, we will have highlighted points along the curve. So we would have a point that corresponds there. Maybe that one's a little too far over, but there will be a point there and another point there. Let me indicate where for x equals a. So you have these points, right? And I'll just do it along this little arc here. And what we're going to do is Riemann is always based on an approximation. So you use something finite to approximate something that's infinite, and then you get the infinite by taking a limit of the finite approximations. That, in a nutshell, is Riemann. So what we're going to do, we're going to compute these finite lengths. So connect those dots with line segments, right? And do that along the entire curve. Find the length of each line segment, add them together, that will give you the approximation. And then, to make the approximation better or more precise, make the partition again with smaller and smaller deltas. And what that will do is that will force the x values closer and closer together. Hence, these little line segments will get smaller and smaller. And in principle, as long as your function is well behaved, right? And for us, we'll be precise what we mean in a second. But as long as the limit of our Riemann sums will converge, it will always give us our exact length, right? So the integral comes to the rescue. So then the only thing that remains now is how do we find the length of these things? So what I'm going to do is I'm going to take, so let's say we have like a xk, and then the next one would be like xk plus 1, right? So what I'm basically going to do is, just so that we can see it a lot more clearly, let's pretend we're going to hold a magnifying glass on this portion, just kind of blow it up and see what's going on, right? So I'm going to take this part, I'm going to redraw it over here, just a lot bigger, right? So let's say this is what it looks like under the microscope. Here are the 2 points, and here is my green line segment that I'm going to use to approximate the curve, right? Now when you look at it on this microscopic level, it doesn't look like a good approximation, right? But we can make it better again by making these endpoints closer together and using more of the green. This is just to illustrate how the formula comes about. Right? So let's do this. So and then down here I'll draw the little portion of my x-axis. So this is x sub k, and then this is x sub k plus 1. So like the next x, right, in the partition. And then of course, what we would have are the corresponding y values. Right? So I'm just going to call this one y sub k plus 1 since it corresponds to that x. And then I'm going to call this one, shockingly, y sub k. Right? Well, the question is, how do I find the length of a line segment if I know the 2 endpoints? Right? Well, use Pythagoras. So if we construct a right triangle, like here and here, if I call, in fact, it's not a matter of if, we call the distance here, the length of each subinterval is our delta x. So I'm just going to call that delta x. And then for this fixed triangle, this length here, the height of the triangle will be delta y. So this distance right here, I'm going to call that delta y. Right? Essentially, and if you think about it, this is the notation we sometimes use when we talk about the slope. It would be the rise over the run, right? But here we don't need the slope. What we need is the length of this green line segment right here. And since it is the hypotenuse of a right triangle, good old Pythagoras comes to the rescue. So this, I'll just say like L sub k, right? For this kth interval, the length of that line segment by Pythagoras, I have to square the length of the 2 shorter sides, add them together, and take the square root. Right? So this is what Pythagoras says. So it's delta x squared plus delta y squared, and you take the square root. Right? So what that means is I can then, and if I redo this just like we do for area, where it's repetitive and it's tedious, and we do the same process for each subinterval, I would compute a whole bunch of these, right? And in fact, let me do this just to make it a little clearer, to say, okay, well, it will be different for each of the different subintervals, right? Technically the delta is the same, but the y might change depending on how curvy or not curvy the curve is, right? So if you put those there, kind of looks like this. All right. So then what we can say is, therefore, the length of this curve is, well, not equal yet. It's approximately equal to summing up all of these things. So the sum, as k goes from 1 to n, of all those little line segments. So delta xk squared plus delta yk squared. All right? So, okay, well, what does this really mean in terms of a formula, right? So what I'm going to do over here is a little bit of algebra to rewrite this square root in a slightly different form, right? And so again, just for simplicity, let me write it without the subscripts so it doesn't get too messy. So I have delta x squared plus delta y squared. What I'm going to do under the square root, because I can't take the square root of these terms separately because it's a sum, right? And that's a huge, thing to keep in mind. You don't want it to try to simplify this radical by taking the root of this term plus the root of this term. That is not a property for roots. But what I can do, knowing that if I could get a product there, it would work, because I do have that property for the square root of a product. So what I'm going to do, it looks a little strange, but under the square root, I'm going to factor out a delta x squared. So I'm going to put delta x squared outside, and that's going to leave a 1 there, plus, then I would have to balance the expression by dividing this by delta x squared. So delta y squared over delta x squared is now in parentheses, right? It's like, why would you do that? Well, there's method to it, to the madness, right? And one of the reasons why we can now do it is because we have a product there. And now I can do a couple things. First, I can take the square root of the first factor, which is delta x squared, and then I can take the square root of the sum, right? But now, here, this fraction, both the quantities are being squared, right? The delta y is being squared, the delta x is being squared. So I can use my properties of exponents and say that this is delta y over delta x, the quantity squared. Right? And then our delta is always positive. Right? Since our delta is positive and you're squaring it and then taking a square root, well, it's just going to simplify to delta x. So I have delta x times the square root of 1 plus delta y over delta x squared. So that's what I'm now going to write here, right? So I'm going to replace this this square root with this square root times delta x, right? So this becomes, so our length is approximately equal to this. And now, since this is multiplication, multiplication is commutative, so I can put the root first, 1 plus delta y over delta x squared, and then times delta x, right? Now, this delta y over delta x should remind you of something important in from Calc 1, where if our function is differentiable, as delta x gets very, very small, delta y over delta x turns into your derivative, right? Assuming differentiability, this thing, if I make my delta x very, very small, will converge to the derivative of y with respect to x. And then we know our delta x's converge to dx's, the differential, right? So if I want the exact arc length now, there are two ways I could say it. I could let my n go to infinity, or I could make my delta x go to 0. With our definition of delta, they're equivalent. Because remember, delta x, we're taking our constant delta to be b minus a over n. if n gets very, very large, then delta approaches 0, right? So we could say the limit as delta x approaches 0 of this Riemann sum, right? So it's a bit more to write, and that's one of the things with the arc length. The formula is a bit more. Oh, almost wrote my d there, not quite yet. And then we have our delta x, that quantity squared, times delta x, right? So again, let me now. So if our function is differentiable, so if y equals f of x is differentiable on this interval from a to b, right? And think back to Calc 1 what that means about differentiability. So it's differentiable on this interval. In fact, the open interval, really. Let me take off the, because we don't really define differentiability, at the endpoints. So if our function is differentiable at every point inside the interval, then as delta x approaches 0, delta y over delta x approaches dy dx, right? So what we've done, right, under this assumption of differentiability, we've proved this theorem, right? And this theorem is our arc length formula. Right? And what it says is this. So if y equals f of x is differentiable, right, on this open interval, keep writing the endpoint, but on the open interval a to b, then the arc length, right, the arc length of y equals f of x is given by, right, and we'll use L for length, right, and it's the integral, so what's going to happen that in fact, let me write it down. I'll write it in stages here. So it's the limit as delta x approaches 0 of our Riemann sums. Right, so delta y, delta x, all of that squared times another delta x, and that we know is our definition for the definite integral. So now the integral goes from a to b, but now I have a square root in my formula. The square root of 1 plus, but then I know that the delta y over delta x converges to dy over dx, but it's the derivative of the function squared, and then we integrate that with respect to x, right? So this is another famous formula from for definite integrals, and this is the formula for arc length, right? Now, there's a similar, almost identical formula. Every concept that we've done, all the geometric applications, area, volume, and now length, they have integrals with respect to x, and they have integrals with respect to y. The integral with respect to y, it's exactly the same. I will state it also. So it's all one theorem. So similarly, if x equals w of y is differentiable on the interval c to d, right? So I'm trying to keep the variables and the limits consistent on the y-axis. But yeah, we could have an equation or a curve where x is defined in terms of y, and then the limits are in terms of y, because y is now my independent variable. So if that function is differentiable, then the length of this curve will be the definite integral from c to d, still a square root, still the 1 plus, and now it would be dx dy, right? Because we would be differentiating this variable with respect to this variable, so dy squared, and the integral would be with respect to y, right? So it's literally all I've done is use the new pair of variables that are limits that we typically use for y, and wherever there's an x or wherever there's a y, switch it to x. Wherever there's an x, switch it to y, and this is our formula, right? So it's the same process, and it's very similar to what we've seen with area and volume. The same concept applies now to arc length, right? So these are our two. Now, the nice thing about arc length is you don't have that many formulas or that many techniques. It's really one or the other, right? Because you're finding the length of a curve. If you're going to find the length of two curves, then you apply this formula twice. So there's no variation in that sense. But what the flip side of it, though, is that these integrals, one of these can be challenging enough. All right. So let's take a look at some examples of this. All right. And I think we'll do two examples just for fun, right? So we'll do some examples and see what the process looks like. So I'll just write down I'll take this function, x to the 3 halves. And so the way this one is set up, it appears that we will have to use the formula with respect to x. And then let's say the interval is from 1 to 4. Let's say from 1 to 4. All right. And we want to find the arc length of this. Now, this is a power function. If you sketch something like this, it almost looks like you're a part of your parabola. It has that same kind of shape, right? Not quite as steep as x squared, but steeper than the line y equals x, right? Because the power here is 1.5. So it's between 1 and 2, right? So it basically looks like this. And for x equals 1, let's say the point is there, and then 4 is somewhere out here, again not drawing the scale. And what we're trying to find is the length of this particular part of the curve, right? That arc. And the thing is, the thing about curves, in particular differentiable curves, when you zoom in on them, right? Even though they might be really squiggly, if you get close enough to them, like when I was using that whole magnifying effect, you do see arcs like this, right? You do see arcs, and hence the name arc length. You're finding the length of the arcs on certain curves. Okay, so let's walk through the process. The first thing now is, because of the arc length formula that involves the derivative, that's what we first have to do. So we have to take the derivative in order to set up this definite integral. So in this case, we're going to take dy dx, and that is 3 halves x to the 1 half, right? And this is our power rule for derivatives now. Bring down our power, subtract 1. Next up, let's do what's under the square root. So under the square root, it's 1 plus the derivative squared. Right, so it's 1 plus, and then I have to square this. So it's 3 halves times x to the 1 half squared. Properties of exponents allows me to do this. It's 1 plus 3 halves squared. So you square the coefficient, and you also square the variable. And then another property of exponent says that because I have a power function raised to another power, I'm going to multiply the powers. So the 1 plus the derivative squared simplifies to this: 1 plus 9/4 times x, right? Because we have the 1 half times the 2, that gives us 1. All right, so this is what goes under the square root. Right? Now, with the arc length problems, particularly before you learn about any other, more advanced integration technique, the arc length problems come down to one of two methods. Either you end up having like a perfect square under the square root, or you're going to have to do some kind of substitution maybe, right? Now, the quantity 1 plus 9/4 x is not a perfect square. Right? So we're going to use a u sub, and what I'm going to use is the entire expression under the radical. Right? So I'm going to let my u be 1 plus 9/4 x. Right? Now, that function that's under the square root is a linear function. So when I differentiate it, I know I'm just going to get a constant times my differential. And constants are easy to adjust, right? So this is 9/4 dx. I don't have 9/4 dx here, so I'm going to multiply both sides by 4/9. So I will get this. So 4/9 du will replace my dx, right? So let's see what we have so far. Under the square root, we have our u. Multiplying the square root, the dx, right? We have 4/9 du, right? But again, I can't just switch these two things. I have to switch my limits, right? With every definite integral, if I change one part of it, I have to adjust the other parts of it, right? When I say parts, remember that there are three basic things that make up any definite integral. You have your integrand, you have your differential, and then you have your limits, right? So we've adjusted the two, so now let's fix the limits. And we have the equation that tells us how to convert from x to u, right? So when x is equal to 1, u is 13/4, right? Because it's 1 plus 9/4. When x is equal to 4, u is equal to 10, because it's 9/4 times 4, that's 9, plus 1, that's 10. Right? So now I have everything that I need to convert it over. So this becomes 13/4. That's the new lower limit. And then this becomes 10, the new upper limit. Let me put those in parentheses, right? So all the things in blue now, having all of those four things allows me to write down this new integral. Why did I write L? So it's the integral from 13/4 to 10, and now I just have the square root of u, which I'll write immediately as u to the 1/2, and then I have my constant here, 4/9 du. And now I evaluate this, and that will be my length. So I can take out the 4/9, that's my constant, use my power rule, but now it's the power rule for anti-derivatives. So when I anti-differentiate this, I will get 1/3² times u to the 3/2, and that's evaluated at 13/4 and 10. Well, we have 4/9. The reciprocal of 3/2 is 2/3. And then let's plug in our upper limit. So it's 10 to the 3/2 minus 13/4 to the 3/2. Right? And again, both of these are irrational numbers. They're not going to work out to be nice integers. So we have 8 over 27, that's my constant. Now 10 to the 3 halves, that's 10 root 10. And then similarly, 13 over 4 to the 3 halves, that's 13 over 4 times root 13 over 4, right? Now, but root 13 over 4, let me do this off to the side here. So we have this. So we would have this times root 13 over 4. But now I can take the square root of 13, and then the square root of this 4 is 2. So in the denominator, I actually have an 8. So if you kind of reduce this to its kind of lowest radical form, it's 13 root 13 over 8. Right? Now, if you wanted to factor out the 8, you could, and this is what it would look like, or I should say 1 over 8. You'll have 8 over 27 times 1 over 8, which means you have to multiply this first term by 8. So it becomes 80 root 10 minus 13 root 13, and then these 8's reduce. So here is kind of the, this is like if you go to some of those online systems, and you might see this as the exact arc length of this function, right? And there it is in all its glory, right? So arc length is not for the faint of heart, right? In the sense that in order to even set up the integral, we have to do some derivatives, right? We didn't have to do much with the other types of applications, right? The most we had to do, like with the disk or washer, we had to square the function. But that was an algebraic process. In the shell method, we had to multiply by 2 pi x. But again, multiplication, that's an arithmetic or algebraic operation. Now having to take the derivative first, that is an analytic or a calculus operation. All right. Okay, so let's do another one of a slightly different form, but it's a nice combination of some of the topics that we've done up to this point. Let's say here's my function now, and it's going to look like one of those area functions, right? Where you have a constant and then you have your x there. And here is the function. It is 9 cosine squared of t plus 6 cosine of t dt, right? So you can think of this function as being some area function, and we want to find the length of the area function. That just sounds strange, but fun to say it anyway. I'm going to find the length of area, right? But it's the idea. The thing is, even though it has an integral in it, it's still just another function, right? And in fact, the fundamental theorem of calculus tells us that this function is differentiable, right? These functions are differentiable, right? So let's find the derivative. So dy dx, well, we know by our FTC that when we differentiate this, we're just going to get the original function evaluated at x. So the derivative, so there's not a lot to do here except using that awfully important theorem, right? So that's the derivative. And again, I always like to do the setup of what's under the square root before I go straight to the arc length problem. So I tend to spend some time doing either the algebra or the calculus that's needed in this step. And then let's take 1 plus the derivative squared. Well, what's nice is if I square this square root, in fact, let me write it down. If I square this square root, the root goes away. right? Now I'm going to end up with, and let's write it in the decreasing powers. So we'll have 9 cosine squared plus 6 cosine of x plus 1, right? And then we're going to have to put this under a square root again and integrate it, right? But again, before we set up the integral, let's see what we can do to simplify this, right? Because remember, this is what we're going to have to integrate: the square root of 1 plus the derivative squared. So the question is, how does this crazy function that's now under the square root, how does this get simplified? Well, it goes back to something I said earlier. In these arc length problems, one of two things must happen for us to be able to evaluate these problems. We either need to have some kind of u substitution that will work, which I don't see how we're going to get a u sub out of this, or what's under the square root has to be a perfect square. And remember, the form of a perfect square is, it's either, like, if it looks like this, a squared plus 2ab plus b squared, that always factors as a plus b, that quantity squared. And if you have a squared minus 2ab plus b squared, that factors as a minus b squared. So basically, the way you can check to see if a trinomial is a perfect square, the middle term has to be equal to 2 times the square root of the first term times the square root of the last term. And that's exactly what we see here. If I take my a to be 3 cosine x, so the square root of this would be 3 cosine x. The square root of 1 would be 1. So if I take 2 times 3 cosine of x times 1, I will get the middle term. So you have to look closely. You have to be able to identify perfect squares, right? Otherwise, you're going to miss it, and otherwise you're going to try to do something crazy that just doesn't work, right? So the important thing here is that what's under the square root is the same as 3 cosine of x plus 1, that quantity squared, right? This is a perfect square. And what happens when you take the square root of a perfect square? They cancel out, right? Because they're inverse functions, right? The power function 2 is the inverse function of the square root, and vice versa, right? So this simplifies to 3 cosine of x plus 1. So this is what we have to integrate, and let me remind you, the limits of integration, x goes from 0 to pi over 2, all right? So now let's actually set up the arc length. So the arc length is the integral from 0 to pi over 2, and this is what we integrate. So 3 cosine of x plus 1 dx. So the actual integration that we have to do is fairly easy. It's relatively easy, but it's this key step. Well, two, I would say, really big steps. One, using the fundamental theorem in order to find our derivative, and then simplifying the 1 plus the derivative squared and recognizing that it's a perfect square. So the arc length is this. Antiderivative of 3 cosine x is 3 sine x. Antiderivative of 1, that's x. And then we evaluate at 0 and at pi over 2. So at the upper limit, 3, the sine of pi over 2 is 1. So we'll have 3 plus pi over 2. And then at the lower limit, both terms evaluate to 0. We'll have 0 plus 0. So the arc length of this curve is whatever it looks like. It's pi over 2 plus 3. And in terms of units, it would just be units because it's length. Units squared, those are applied to area. Units cubed, those are applied to volume. With just units, that's applied to length. All right. So two, I think, good representative examples of, the type of work that has to be done when you're computing arc length. And sometimes the algebra gets a little bit more challenging. So, we'll just have to work through it carefully, following our steps, right? See you in the next video.